welcome back, everybody. Is this the second week of class? It's the second week, right? We had the first week last week, and now we have sort of class number 5. Well, I hope everybody has had an okay time making it through the first couple weeks, and luckily we're headed into the weekend now shortly. Okay, so as always, going to do a little bit of review. So last time we talked a lot about latent heat. So latent heat is this idea that, so water is a very interesting substance, not like a lot of other materials, because it exists in all three of the main phases of matter, liquid, solid, and vapor phase at the Earth's surface. And then the key idea that's really relevant for climate is that when you transition between these different phases, go from ice to liquid water, or liquid water to vapor, there's a lot of energetic exchanges involved, and these things are called the latent heat. So there's the latent heat of melting is the amount of energy you have to put in to transform a sample from water ice to liquid water. It's about 80 calories per gram. But then the big one is the latent heat of vaporization. And this is the amount of energy in calories or joules or whatever unit you like they have to put into a sample of liquid water. This would normally be happening at the surface of the ocean, and transform that into water vapor, which then goes into the atmosphere. And we talked about this in the context of evaporative cooling. So essentially when you have evaporation happening, it's the fastest molecules in the sample. So the molecules in the sample, they move at all these different speeds. It's the very fastest ones that have enough velocity that it's kind of like they have escape velocity, that they can break the intermolecular bonds like hydrogen bonds and van der Waals forces that try to keep water in liquid coherent states. And so you have these fast molecules, they tend to leave. And then what that means is that those fast molecules, with their high amount of energy, are stored in the atmosphere. And so this latent heat of vaporization of 540 calories is stored in the air in the form of water vapor. And that energy came from the surface ocean. So that means that when you have evaporation, it actually cools the surface ocean. On the first assignment, you get to actually make an estimate of how much it cools. And that's called evaporative cooling, and it's the same reason that humans sweat. When your sweat evaporates, it helps you cool down on a hot day if you're playing tennis or whatever. And the same process works in reverse. So when you have clouds, so in clouds, the water vapor, which is invisible, condenses into water droplets, which are visible and form clouds, and that energy of latent heat of vaporization gets dumped into the atmosphere as heat energy. It warms the atmosphere up, and that has a big effect on thunderstorms, cyclones, hurricanes, things like that, that we'll come back to just in a few lectures. We'll be talking about hurricanes. Then we also moved on to talk about what factors influence the density of water. And so this got us to this idea of the equation of state. And so usually we denote the density as this Greek letter rho. That's the mass of a sample divided by its volume. And just like it's the case for an ideal gas, there are these relationships that relate the density to the sort of more fundamental thermodynamic properties like the temperature or the pressure. And so for fresh water, the density is a function. This F just means a general function, so some kind of relationship here between the pressure of the water and the temperature of the water. So the way it works is, if you tell me the temperature and the pressure, I can tell you the density based on this formula. That might be a computer program, not a simple like pencil and paper formula, some kind of code or a spreadsheet, but there's some kind of relationship between these two variables and this variable. And now today we're going to extend this idea to look at how it works for salt water, which is very, very conceptually similar, but a little bit different because we have to deal with salinity. And then we talked about the concept of salinity itself, and so salinity is how we measure or quantify the amount of salt that's in a sample of seawater, and we usually call that S. And the definition of the salinity S is the mass of salt in a sample divided by the total mass, including both the salt itself and the water molecules. And so this is usually measured in parts per thousand, and on average, a very, very common type of number is that if you have 1 kilogram of water, there's about 35 grams of salt, which is mostly sodium chloride, but also has a mix of other things. Okay, so today we're going to talk about the density of seawater, so move on from fresh water to incorporate salinity. Buoyancy and Archimedes principle, so these are effects. Buoyancy basically causes motion or causes things to float, depending on their density. That obviously is tied into salinity because salinity affects the density. And then we're going to get into how is the salinity set and how does it vary. So what are the actual physical processes in the climate system that modify salinity? As you can imagine, things like rain is one of them. Rain changes the salinity, as does evaporation. And also sort of doing a little bit more sort of ocean geography. How does the salinity actually vary as we look around the climate system? Okay, so we talked about this last time. Here's the definition of salinity, and this is sort of the pie. So you have mostly, if we take, here's our 1 kilogram of water, we've got 35 grams of salt. It's mostly chloride and sodium with some other small components. And last time we sort of concluded with a discussion about how could we measure this. And there were a few suggestions. So one really simple suggestion is you could just boil the water and the salt is left behind. And by weighing how much salt you have after you boil away the seawater, you can estimate the salinity. That's quite accurate, but it's not accurate enough for quantitative purposes. And then we ended with this other idea, which is called the principle of constant proportions. So what this means is that if you look at a sample of seawater, you see all these different types of salts dissolved. But even though the overall amount of salt varies from place to place, and we'll see how it varies, the ratios, the relative ratio of chloride to sodium to sulfate to whatever, those ratios remain quite constant wherever you look. So the overall level goes up and down, but the ratios stay the same. And the reason for that is that the ocean has been stirred up over millions of years, and these ions, all these ions, they remain in the ocean for a long time, about 50 million years, but it only takes them about 1,000 years to get mixed up. So they get mixed up many times. And if you think of a salt ion, here's the salt crystal. He explores the whole ocean many times, and so he meets up with all these other ions. They all hang out in the same ratios all the time. So what that means is if we could measure any one of these, say maybe chemically, we could infer all of the rest of them and then add up the total salt, and we get the salinity based on that. So that's the idea of the method of constant proportions. It turns out that chemically, the thing that's easiest to measure is the chlorinity, or the amount of chloride ions in the sample. And I think you guys are probably more familiar with this torture device than I am. But so you basically drip down stuff, and eventually there's a color change, and that tells you how much chloride was in there. And if you look at the fraction of chloride, the chlorinity is about 55%. So that's, it's a little bit more than half, so about 55% of the pie is chloride. So that means that the chlorinity is 55% times the salt, 55% of the pie. And if we just divide by that 0.55, we get 1.8. So the S is equal to 1.8 times the chlorinity. So if you can measure this chlorinity using this titration setup, you can infer the salt from that. So that would be a chemical analysis. Another method that was mentioned was electrical conductivity. This was the first suggestion. And this is the standard way. Essentially, in real oceanographic practice and in any research lab, this is always the way that it is done. It's only done using conductivity, except maybe a high school science project might use the boiling method, which would be accurate. And so this sort of shows a very sort of cartoony schematic of how it works. On the right-hand side, these little dots are meant to represent salt ions. Of course, they're invisible, really. But so there's ions in this one. This one's fresh water. And if you put an anode and a cathode, so you take two electrical, rods, two conducting rods, attach it to different ends of a battery. Current will actually be conducted through the water relatively easily in the salt water, whereas in the fresh water, it won't happen to as great an extent. There's some conductivity. But so the light bulb is going to be brighter for the salt water than for the fresh water. So measuring the conductivity is in practice a very highly accurate way, and it's a very practically easy way now of measuring the conductivity. But just to bring a little bit of sort of fundamental physics into the picture, does anyone have any idea how do we measure electrical quantities? Like how does one measure electrical current, for example, or resistance or voltage or anything like that? Anyone have an idea? Because measuring mass is pretty easy. You can put it on a scale, compare it to some known mass, balance them out. But how about for electrical current? Has anyone done this in a lab, maybe, at any point? Measure the current in a wire. So how was it done in the lab?
By looking at the magnetic field around it.
Looking at the magnetic field. That's exactly right. Yeah. So what most people say is, when I ask this question every year, the answer that I usually get is using the multimeter. which is true, but that doesn't get to the actual physical principle that's involved. But the principle exactly involves the magnetic field. So there's various ways to do it, but for people who have taken physics 1051 or maybe 1021, this is not detailed content that's going to be tested, but just so that we sort of know here. So when you have a current that flows through a wire, so we mentioned there's it's not just a segment of wire, it's attached to a circuit or a battery somewhere down here. So when the current flows through the wire, there's actually a magnetic field that's generated that circulates around the wire in this circular pattern. And so if you imagine a circuit like this, so here we got, this is a battery here. If you're not familiar with circuit diagrams, it's a little resistor, and there's a switch here. So you close this switch, and now the circuit is active, and the current is going to go around the circuit. So if you have a compass needle that's near that wire, and you have a strong enough current that's going to generate a decently strong field, when you close this switch, this magnetic compass needle, which normally points north because of the Earth's magnetic field, if you generate an electrically induced magnetic field nearby, that's going to be stronger than the Earth's magnetic field, and it'll tip over the compass needle one way or the other, depending on the direction of the current. So by basically making a device where you have sort of a magnetic object that gets tilted, by measuring how fast it tilts or maybe how much it tilts, you can measure the current that goes through the wire. And so that's sort of the general principle that's involved in the inside of a multimeter. There's one more method that I know of that's commonly used to measure salinity. And this is usually the one that no one mentions unless they own tropical fish. Does anyone here have fancy fish that they keep as pets? Or a fancy aquarium, or know anybody? No? I had one person last year. So it turns out you can also measure, so if you keep tropical fish, you need to have water that has the appropriate salinity for them. It turns out you can use the principle of refraction to measure the salinity. So refraction means that when light passes between two mediums, so say maybe it passes from air traveling through air to traveling through water, the light rays bend when they go from one to the other. You might have seen it in physics where it's called Snell's law, so maybe in high school also it's covered. And this is the reason, if you've ever looked at a situation like this where you have a cup of water, so this is water down here and then there's an air layer at the top, and there's a straw going in, that the straw appears to be broken right at the interface. Obviously the real straw is continuous, it's not broken. But because of the way the light rays bend as they go between this interface, when you're viewing it from the side, it looks like there's this sort of jump in the straw, and that's called the bent stick effect. And it turns out that the amount that the light rays bend, sort of how dramatic this effect is, depends on the salinity of the water. Meaning somehow you could make a calibrated device that measures the salinity based on this principle. And this thing is called a refractometer. It looks like this. And this is used very commonly for bulk reefs. You can get these from a pet store. And what you do is you take a couple of droplets of your seawater or your seawater that you've made. You put it in the front, and you close this flap, and then you just look through your eye. Your eye goes in here, and you look through the column here, pointed at a light source. And what it looks like is like this when you look through it. So you'll see, I guess the water here and the air here, and the salinity is just measured on the side. So in this case, this sample would be a little bit more salty than normal ocean water, about 40 parts per thousand. So that's not really practical for oceanography, but the key idea is anything that salinity affects, like it affects conductivity, it affects refraction, you can somehow, based on that, make a calibrated device that you can use to sort of back out the salinity based on whatever measurement that is. And that's just a general principle of measurement devices. You find what does this quantity that I want to measure, what does that affect? And if you can measure that effect, you can back out the salinity. So the refractometers are not used for scientific oceanography, but they're a really quick and effective way of doing it for pets. Okay, so one of the reasons, the main reason in terms of physical oceanography that we care about the salinity is that it affects the density, and then the density affects how water moves. It affects the ocean currents, affects sinking of water, convection, etc. And so it's a very important part of modern quantitative scientific oceanography to quantify how the salinity controls the density. And so there's really three, and so this is called the equation of state of seawater. So previously we talked about the the equation of state for gases, which is the ideal gas law, and we talked about that simple F of pressure and temperature, which is the equation of state for freshwater. So for seawater, there's now three effects. There's the temperature and the salinity. Those are by far the two most important, but pressure also plays a role. But if you want to be really, really detailed and be accurate enough for modern quantitative oceanography, you include everything. And so this equation of state for seawater is extremely complicated. And actually, they put out books just describing what the relationship is. And so this is the most recent book. So the most recent internationally accepted consensus equation of state for seawater came out in 2010. And this is the manual for that. This is a 200-page manual. I don't think any one person understands all of the physics that's involved, but you can just download a script in Python that runs this for you. So you can just get a computer code that implements all this, and that's done by every oceanographer every day. And this thing is determined using some combination of like thermodynamic theory, a lot of experiments, and then all the calculations are done on the computer. But so that's very, very complex, and in my sort of advanced course, I get them to mess around with the code and do some plots and things. No one understands all of the physics, but people understand it. It's all understood, but no one person understands it all. But so very often what we do in sort of conceptual oceanography, when we're trying to understand the basic principles, is we use this thing called the linearized equation of state, which is a simplified approximation that takes the two main features of temperature and salinity and makes a simplified model of how the density varies. And so this is how the equation looks. So the left-hand side is the actual density of the sample. And then this equation is calibrated based on some reference point. So we say, let's say we take a reference temperature of maybe 20 degrees Celsius. That would be a reasonably standard surface temperature for the ocean. And maybe S naught, so T naught, the naught there means the reference. And then S naught here is the reference salinity. That might be 35 parts per thousand. And then rho naught here is the density that we measure of seawater that's at that particular temperature T naught and that particular salinity S naught. And so you can see if you set the and then T without the naught is the actual temperature of the particular sample that you're interested in, and S is the salinity of that sample. So the way that the equation works is if you tell me the temperature you're interested in and the salinity you're interested in, and the values of these constants, so alpha, beta, T naught, and S naught are all constants. If you plug in T and S, then you can work out the right-hand side of this, and it'll give you the density at that particular temperature and salinity. And the equation is sort of encodes a little bit of the physical understanding because we can see that there's two terms here. So the density of the sample equals the background density multiplied by this expression. We have 1 minus alpha, which is called the thermal expansion coefficient, times that's something to do with temperature, plus beta, which is called the coefficient of haline contraction, times something that has to do with salinity. But the key thing to notice is that there's two different signs here in the two terms. So the first term has a minus sign, minus alpha times T minus T naught. And then the second term has a plus sign, plus beta times S minus S naught. So what that means is if you make the temperature larger, yes?
On an evaluation, if we would be asked to solve using this equation, would we be given coefficients?
Oh, absolutely. Yeah. So that kind of thing could happen, and then all of this would be all the exams and stuff. You always have a formula sheet, and any kind of constants that you need will be on the formula sheet. And usually, if I can, I try to give you the formula sheet a couple of days before the exam, so you kind of know what you're working with. But yeah, you always begin. You never have to memorize any number. Maybe. You're not going to have to memorize any number. So what I want to emphasize is that there's two different signs. So the first sign is a minus sign here. What that means is if you imagine temperature increasing, so let's say the T is going up. So what that means is that you're subtracting off a number from the density, and that number is getting bigger and bigger. So as the temperature grows, that means the density is going down because you're subtracting off a bigger number. Whereas this one has a plus sign, meaning as you increase the S, this thing's getting bigger and bigger, and you're adding it on, so the density is going to increase. So salinity, that's why it's called haline contraction, because when you add salinity, it's almost like it makes the water contract. This is kind of not really perfectly true. You'll see on the assignment. But adding salinity causes the density to increase, mainly because you're just putting more stuff into the water. You're dissolving salt in. The salt goes into the inside of the sample. It increases the density. So we add more salt. This term gets bigger. You're adding it on, so the density increases. Whereas when you increase the temperature, it causes the water to expand, just like the thing if you run a jam jar under the hot tap, it causes the metal lid to expand. So the same thing is true of seawater. So you increase the temperature, this term becomes larger, it's got a negative sign, so you're subtracting it off, and so that means that the density is going to decrease. And so we have these two phenomena, temperature, which tends to make the increasing temperature makes the density go down, and increasing salinity makes the density go up. And understanding those two directions and sort of the basic physics of why that happens, that is exactly the kind of thing that you could get on an explanation question or multiple choice question. So that is very important. Because those two principles, thermal expansion and haline contraction, allow you to, if you're looking at, say, salinity or temperature data, make some inference based on that as to how the density should be changing. Okay, so that's the basic picture of how salinity affects the density. And density is something we care about a lot because it affects the physics of the movement. We're now going to move into, first, how does salinity affect the buoyancy, or how do these density effects affect buoyancy of water particles, meaning sort of how they float or sink. And then we're going to move on to how does salinity vary across the ocean. Okay, so the average number for the ocean that's worth keeping in mind, although you wouldn't have to actually have to remember it, but it's nice to keep in mind, is 35 parts per thousand, so 35 grams of salt in a 1 kilogram sample of water. But over the ocean it varies for lots of different physical reasons. We're going to talk about those. And so it tends to be that if you're near the coast, so not the open ocean, but near somewhere where a river flows out into the ocean, then rivers have some salt and some nutrient content, but generally rivers are very fresh. And animals drink from rivers and that sort of thing. And so river water is pretty fresh, so whenever you have a river outflow, you tend to have what are called brackish waters, which are much less salty. And a typical value for brackish would be about 10 parts per thousand, so 1/3 as salty. And then there are also certain parts of the world where you have what are called hypersaline conditions, just meaning much more salty than normal, and it can be much, much saltier. So for example, you may have heard of the Dead Sea. So here's Jordan, and here's the West Bank here. And the Dead Sea is essentially a landlocked saltwater lake, and that has salinity up to 330 parts per thousand. So that's 10 times more salt concentration than we have in the open ocean. So this is a photo of somebody floating in the Dead Sea reading a newspaper. So because the water is so salty, the density is higher, and that makes it easier to float overall. So you find when you swim in the Dead Sea, which I have never been here, but my wife has, and you're very, very buoyant. It's sort of a weird experience, according to her, swimming in the Dead Sea. And so just to think a little bit about the physics of buoyancy, something that really strikes me about this photo is that the lady here, she's reading the paper, and she's got her legs actually stuck out of the water here. So does anyone know, or have a guess, or have a physical idea? When you put your legs out of the water like that, does that make it easier to float, or does it make it more difficult to float? Easier. So why do you think that?
I don't know. I guess because all the particles or whatever are underneath it, so that you're kind of just laying on top of it as opposed to being under it. Then you get everything above it and below it and to the side of it.
Okay.
I don't know if that makes sense.
So that's an interesting idea, and I think it illustrates that this is not an obvious question because it turns out it's actually harder. It's harder, and so the fact that her legs are outside actually is illustrating just how buoyant she is, because if her legs were underneath, she'd be even more buoyant and would be sitting higher in the water. And so here's the reason. So, and we're going to talk about the principle of buoyancy now on the next slide, but you float in water because your body is less dense than the water. If you were more dense, like a rock, you would sink, right? And it's the density difference that helps you float. And so people have gone swimming probably at some point, maybe at a pool like Aquarina. Does anyone know if people know what a flutterboard is? Flutterboard? Yeah. So it's basically a piece of styrofoam, and it helps you swim around. It's very, very buoyant. So have you ever tried to hold a flutterboard underwater? It's fun, right? It's very hard to do because if you let it go, it'll hit you in the face. Right? So flutterboards are very, very buoyant, and the reason they're so buoyant is that styrofoam is much less dense than water, so it's very buoyant. So the same principle is true of the human body. So your body is less dense than water, and on average, parts of it are more dense than water, but on average it's less dense. So if she took her legs and put them in the water, it's like a less exaggerated version of putting a flutterboard underwater, because her legs are less dense. So when you put them underneath, it's like a slightly less aggressive form of a flutterboard, because these legs are less dense than the water. So when they're submerged, there's a buoyant force that pushes you back up. So the more of your body that's submerged, actually the more buoyant force you feel. And so actually it's more difficult to stay afloat the more of your body is above the water line. And the reason is that the force that's pulling you down is the force of gravity acting on your whole body. So whether your legs are above the water level or underneath, gravity is still pulling you down. But the amount of buoyant force you get is based on how much of you is submerged. So if that flutterboard is sitting on top of the water, it's not getting pushed up. But if it's under the water, it is getting pushed up. So it's easier to stay afloat if these were underneath. And the fact that she can do it and float so comfortably as to read the newspaper is just sort of showing how salty that water is and how dense it is. Okay, so the fundamental physical equation that governs this is called Archimedes' principle. So Archimedes is this is a artist's rendition, obviously. So he lived, more than 2,000 years ago, and he was a very early mathematician and scientist who did a lot of very impressive things in physics and science. Basically, well before Newton and well before we had anything to work with, he sort of had to invent everything himself. And you may also know this person. There's this story of somebody who's in the bathtub, and then they say Eureka because they figured something out. That's this guy, it's the Eureka guy. And the whole Eureka thing was about this principle of buoyancy. So the question is, we all know that when you put the flutterboard underneath or you're swimming, you experience a force that prevents you from sinking. That's called the buoyant force. But how strong is that? Exactly, how can you calculate the buoyant force? And the formula is that the force of buoyancy, and this can be proved, but we're just going to state the result. So the force of buoyancy, F sub B, is equal to the mass of fluid that you displace with your body. So the total amount of mass of water that you're pushing away by virtue of being submerged, multiplied by gravity, that's the force of buoyancy. And very often, in practically every problem, like homework problem, we don't just work in terms of the mass, we work in terms of the density. So if you have a certain volume of the object, so this might be the submerged volume of the person, that volume multiplied by the density of water, that's the total amount of water, mass of water, that you are displacing, and then multiplying that by gravity, and that gives you the force of buoyancy. Okay, and that's Archimedes' principle, and you'll definitely have, I think this is not on the first assignment, but on the second assignment you'll have some exercises playing around with this. And this course is very important piece of physics, because not only does this apply to objects like a flutterboard or a beach ball or something that you put in water, it also applies to parcels of water themselves. So if you have a little cube of water that's maybe warmer or saltier or somehow different than its surroundings, it will feel buoyant forces based on this same exact formula, and that controls a lot of vertical movement of water, like whether water's going to rise to the surface or whether it's going to sink to the bottom, both of which happen in different locations. Right, so this is just this almost for your notes. So based on this buoyant principle, this force, the less of your volume that is, so the volume displaced is the total amount of your volume that's underneath the surface of the water. And so to make the maximum buoyant force, you want the maximum amount of volume displaced. And so in this case, if she put her legs underneath, that would cause a higher buoyant force and make it easier to float. Okay, so now this is a little fun thing. So I can't, my life is relatively boring, but my wife's is not. And so I like to show this example. So a few years ago, Jeanette works in experimental biology, whereas my work is mostly with math and computers and stuff. And so she had a very interesting, in 1 month period, when she worked as a scientist in Zurich in Switzerland. And she was at a conference in Israel, and then went swimming in the Dead Sea, and so it had this very, very strong effect of being really, really buoyant. And then that same month, she went on a parabolic zero gravity flight. And so she had very, very strong negative gravity, basically buoyancy in the Dead Sea, and then had zero gravity in sort of a very interesting flight. Has anyone heard of parabolic flights before, or zero gravity flights? So yeah, so do you just in very general terms, like what's it about, or like how does it work?
Doesn't the plane just drop?
Yeah, so it actually drops and it goes up. So it kind of goes in like an oscillating up and down pattern. The reason it oscillates is because they want to, it's when it drops is when you get the zero gravity. And you can even experience this. There's quite a few places in St. John's where there's like a bump in the road. And I don't know if you've ever experienced this. You go over the bump, and as you come down, you kind of get this like light feeling in your stomach, like you're weightless for a second. So it's that same idea, but on a massively more extreme scale. The plane goes up and down like this in these huge arcs. And then on the downswings, you get essentially zero gravity. And so just as a little bit of, if you're interested in possibly doing research or maybe having a career in science or engineering or technology, I like to show this video, which just shows kind of how cool it is. Let's see here. Parabolic. So this is my wife Jeanette, and these are her scientific collaborators. An interesting thing about these is that they're using this to do scientific experiments. So they have apparatus in the back running analysis. But to fund these things, there's two kinds of people on this plane. There's the scientists on this half, and then there's like the billionaires on the back who pay to go on it for fun. But she got to go on it for free because she's doing the science. So this is her collaborator, Anupam. Yeah, they're having fun. And so what's going to happen is, so right now, gravity is normal, and now they're going to transition from one arc to another. These guys here are pros. They work on the plane, so he's really comfortable. Everybody else gets strapped down. And now, in a minute, the plane is going to go into zero gravity mode. He's preparing for it. He's getting ready. Isn't that cool? Yeah. And so they do fun things like they're throwing the ball around. I think in a moment, this guy throws the ball and tries to hit him in the groin with it. I thought he threw that. Oh, here we go. And so now, how it actually works is you oscillate between having zero gravity and having hypergravity. So on the way down, the gravity is zero, you float around, and on the way up, you weigh twice as much as you normally would, so you're sort of smashed into the ground. And the people that are used to it, they walk around all casual, but this was really fun, and they got to do this numerous times. I think up and down they went, maybe 10 or 12 times. And they actually had what they were doing. The purpose of this was they were using. So why would you do this? What's the point? And the point is that what Jeanette works on is how bacteria in the ocean behave. And you can imagine, so in the ocean you have like waves and stuff that are causing things to rise and fall. And if you're a little tiny bacteria, there's a wave that comes by, you're getting brought up and down at this very, very large scale compared to your body. And so the idea was to look at how do bacteria behave in these fluctuating gravity fields. And they had an opportunity basically to kind of get some money to go on. There was a funding call to go on this zero gravity flight. They thought, okay, we can use that to study this thing. It was partially cool scientific idea, partially all the scientists wanted to go on this plane. So it's a little bit of both. Okay. So now a bit of a transition. So salinity affects the density of water, and then the density affects the displacement of mass, and so that affects the buoyancy. But now we want to talk about how and why does salinity vary from place to place. So the average number is 35 parts per thousand. We know near river outflows it's less, but what are sort of the processes that affect salinity? And so there's a few of them. So the first slide here is things that are going to decrease the salinity and make the water fresher, and then the next slide is things that are going to make the water saltier. So some of them are pretty obvious. So precipitation, like rain and snow, so we have precipitation that falls on the surface. Precipitation is very, very fresh water, so it's essentially purely fresh, so there's no salt in this rain. And so as you add fresh water to the surface, that's going to dilute the salt that's there already, and that decreases the surface salinity. But in terms of the principle of constant proportions, you think, when you add fresh water, it doesn't change the ratio of chloride to salt, because those things are steady, so that preserves that principle of constant proportions. Runoff, so if you have some river that discharges in the ocean, that also adds mostly fresh water and also some nutrients, and so that decreases the salinity by dilution. And then ice melting. So ice in the climate system comes in these two forms. It comes from sea ice and then glacial ice. Can anyone tell me the difference what's the difference between sea ice and like icebergs or glacial ice? Yeah.
Or sea ice is just like chunks of ice that form naturally from like the seawater, where I think icebergs are from like glaciers up further north.
Correct. Yeah, exactly. And also from Antarctica, but the ones that we get are from Greenland.
Yeah.
Yeah. So icebergs are pieces of glaciers that break off. So Greenland is covered in ice, and so is Antarctica. And at the edges, chunks of ice break off and float away, and those are called icebergs. Whereas sea ice is frozen seawater. So the upper layer of the water, if it just gets very cold, will freeze into these layers. And so this is sea ice, and then this is not a real picture of an iceberg, but looks something like that. But in both cases, the ice is fairly fresh, meaning there's relatively little salt ions embedded into the structure of the ice. Glacial ice is extremely fresh, essentially pure, because glacial ice forms from precipitation. Like basically it snows on the top of a glacier, that's precipitation that's extremely pure, and then when it breaks off on the side and forms an iceberg, it's just as pure as it started. So icebergs are extremely fresh, and actually in the past have been used as a source of fresh water. You can capture icebergs and then drink the water. Whereas sea ice, because it forms from seawater, which is salty, has some salt embedded into the structure of the ice, but salt doesn't like to go into the ice structure because it doesn't kind of match with the hydrogen bonds and things. So when you form sea ice, most of the salt actually falls out the bottom and doesn't get incorporated into the ice. So the sea ice is also still fairly fresh, and so when this melts, it releases fresh water into the surface ocean and lowers the salinity. But the opposite happens when it forms, and so now these are some examples of processes that increase the salinity. So precip, we said precipitation, fresh water dilutes it, and so lowers the salinity, but evaporation is the opposite. So in evaporation, you've got sort of the sun coming down in a hot atmosphere, and so just like we said, so water molecules leave and go into the vapor phase. And so we have less fresh water left behind, and so whatever salt was there is now more concentrated, so the salinity goes up. And then in the process of sea ice formation, it's the same principle. Because the sea ice doesn't like to incorporate salt, when you form that ice layer, the water that's left just below that sea ice is now saltier because the salts are left behind and you removed some water. We'll talk about this in a bit more detail later. This is also called brine rejection. So if you want to find really salty seawater, if you look underneath the regions where sea ice is forming, you kind of have this sort of halo of really salty water right underneath this sea ice. And so sea ice kind of works both ways. When it forms, it makes things saltier, and then it melts, it makes things fresher. Okay, and so these processes, precipitation, evaporation, ice, runoff, they happen all over the world at different rates depending on exactly where you look. And so what that leads to is a distribution of salinity globally that is not constant, so it depends on space. And so some places are saltier than others, and there are some general principles that tell you, oh, on average, where is it going to be saltier and where is it going to be fresher. So this cartoon shows kind of an average picture of, as a function of latitude, so where you are, so this is the South Pole is 90 south up through, all through the southern latitudes, 20, 10, equator is 0, and then the positive latitudes up to 90 north, the North Pole. So as a function of where you are in the sort of north-south direction, what's the average salinity? And that's the green curve here. I'm also showing that the temperature. The temperature is very, very simple. It's warmest at the equator, and it's coldest at the pole. So you just have a sort of this kind of curved shape with a maximum right at the equator. But salinity is more interesting. So generally, you would probably think that salinity is going to be highest where we have the highest evaporation. So wherever you're going to have the most sunlight, hottest atmosphere, you're going to be evaporating that fresh water from the surface, concentrating the salts. And that's what we find. So in this tropical region between about 25 south and 25 north, this is where overall this green curve is higher. So it has higher salinity values here compared to the poles where it's lower. But there's some interesting structure where actually the two peaks of salinity aren't right at the equator. It's at the Tropic of Cancer and the Tropic of Capricorn, so about 25 north and south. Those also tend to be the latitudes where you get the world's most significant deserts. So like Death Valley, lots of California is around here north. Major deserts in Iran and in China are at these latitudes. And at the poles, we have less evaporation because the sun is not as strong, and also because the atmosphere is colder. And also, you have lots of land up at the pole. So like, for example, you think about up here, there's all this land in Canada and Russia and Greenland, and there's all these rivers that come and they dump fresh water into the polar regions, and so you have extra runoff, and so the salinity is lower there. But a very interesting feature is that right at the equator, the salinity is still high. It's high compared to the poles, but it's a bit lower than the desert latitudes, these peaks here. Can anyone give a guess as to why it is that the salinity has a little bit of a dip at the equator? It's something we mentioned a couple classes ago, that there's something happening right at the equator that could affect this. Does anyone remember or have an idea? Yeah.
The high precipitation.
Yeah, and is there a name associated with that?
Intertropical convergence.
Oh yeah, it's right there on the slide. I'm stupid. Yeah, so if you look right at the equator, we showed this diagram before. So blue means heavy precipitation. So right along the equator, we have this strong band of precipitation. We're going to cover that probably next class, why it's there. But so you also have high clouds, which blocks the sunlight, so you have a little bit less evaporation, and you have this strong precip there. And so right along these 30 north and 30 south, we've got these red blobs. That's where we have deserts, and also that's where we have the saltiest surface waters. And the equator is a little bit fresher, still relatively salty, but it's a little bit fresher because we have lots of extra precipitation in that region. And if you want a more detailed view, that's not just sort of the average around a latitude circle or the global average, this is from satellite data. So it's also a little bit of a cartoon, but so the red regions mean it's saltier, and then the blue regions mean that it's fresher, and then green is in between. And so we can see here the same basic ideas that we have around 30 north and 30 south. We've got these red bullseyes. In the Pacific overall, you can tell from this color map, is a little bit less salty than the Atlantic in general. So the Pacific is just a fresher ocean that actually has really important implications that we'll get to. And even in the Indian Ocean, we have around 30 south, strong surface salinity features there. And you can see also right along the equator, we've got this sort of band where we have weaker salinity, and also you can see it in the Atlantic, and that's associated with the ITCZ. Does anyone have any idea? So this kind of measurement, where we somehow look at the whole Earth at one time from a satellite, is generally called remote sensing. And this differs from the earliest ways that we measured the ocean, which was basically you take a ship and you go around with the ship and you take a bottle and you sample the water from various locations, and then you take it back to the lab and you measure it, and then you make a map of salinity. That is extremely expensive because the kind of ships that you need and having a captain for the ship and deckhands and all that stuff, all the people involved, it's a really, really expensive. That in oceanography, that's called ship time. And if you apply for research grants that require ship time, it's hundreds of thousands of dollars. Now, satellites are more expensive than hundreds of thousands of dollars, but then they basically work for free once you set them up, whereas every measurement from a ship costs money individually. So this whole area is called remote sensing, where we sort of look at the Earth from space and try to get whatever data we can. A lot of this was developed by NASA and the Jet Propulsion Laboratory in California. Does anyone have an idea, how could you possibly measure salinity from space? I didn't know this until this morning. So does anyone have an idea? What possibly could you use? I'll make one thing that we measure from space is chlorophyll. So if you want to study something like probably plankton blooms, many of the marine biology students have probably heard about plankton blooms before. And you can actually see with a very high quality camera, you can actually see that the ocean is slightly greener from space, and you can see the chlorophyll directly. And then basically based on calibration type systems, you can measure surface ocean biology just based on ocean color. But salinity is invisible, so it's a little bit less obvious how you would actually do that. Anyone have any idea? Not obvious at all. How about temperature? Does anyone know how we can measure temperature? This is also done. So we can measure sea surface temperature from space. This is showing salinity, but we can also measure temperature. Temperature is a little tiny bit easier. Okay, so we'll come back to this, I think, later. So has anyone ever seen something like thermal goggles or heat goggles or like night vision goggles before, where things show up green and you can kind of see the heat that's being emitted by things? I think it's maybe something like CIA uses this kind of stuff. Like you've seen images of maybe on the internet or television shows. So how those technologies work is every physical object, so like this cup, my own body, if you're at any temperature that's higher than 0 Kelvin, the molecules that make up your body or make up the cup, they're jittering around, and as they jitter around, they emit radiation. And so what thermal goggles do is they detect the radiation that you emit, as opposed to our normal eyes, which detect photons that are scattered or reflected off of what you're looking at. So when we see normally, we're looking at light that comes from that light, hits you, and then goes to my eyes and I can see it. Whereas thermal goggles, I'm looking at things that you guys emit directly. So I see like hot spots for each person. So the sea surface actually also emits energy, it emits radiation, just by virtue of the fact that the water molecules are kind of randomly moving around. Those molecules are charged, so they sort of fling off electromagnetic waves. And by looking in a lot of detail at the precise wavelengths and amount of energy that's emitted by the surface, you can actually measure the temperature. And it turns out that salinity has a very, very slight effect on how much radiation you emit, because it changes those charged particles that are in the water. And very sophisticated calibrations have been developed to actually measure the salinity based on those tiny variations of the energy, the radiation that's emitted by the surface water. So it basically works on the same principle as infrared goggles or night vision goggles. And it's done with very, very fancy, expensive equipment in space, but even though that's very expensive to set up, it's still enormously cheaper than needing to hire a ship to do these measurements every time. Okay, great. So I'll end there, and next time we're going to talk about how salinity changes in the vertical, and then I think move on to the atmosphere, and how the winds blow the ocean around. That'll be next week. So I think now we've covered all of the material that you'll need for assignment 1, so I think you can feel free to take a crack at all those questions. I think it's due on Wednesday, 24th. And feel free to let me know if you have any questions. Otherwise, have a good weekend. I'll see you next week.